Hey guys, I wanted to talk about heat cycles today. Heat cycles are pretty important. The engine in your car, for example, goes through a cycle. It repeats the same motions over and over and over again, and a couple thousand times a minute. And you're taking heat from a hot source, moving it to a cold source, a cold sink. And as that energy flows here, we're trying to divert some of it into work. There is a heat engine here that does that, and you can see kind of like a little process here where this turns into that and things happen. There's several steps and stages of this thing. We want to talk about those stages, and there's always two questions here that we're interested in. How much work do I get out of it, and what's it going to cost me? How much energy do I have to put in it to make it happen? Okay, so that's where we're headed today. This first example, this first little cycle I'd like to tell you about, I'm calling the square cycle. You wouldn't really build an engine like this. This would not be very practical, but it is easy to think about because it's square, right? You got all these nice straight lines right here, and that path around and around and around is the cycle that I'd like us to think about real quick here to begin with. First of all, we're going to start at point A and have an isoquart process up to point B. How would we do that? Well, you'd heat it up. So right here I've got some fire up underneath this thing, or we're burning gasoline or coal or adding steam or something. We're heating this thing, and it's we're not letting the piston move. So that heat's going to go into the form of internal energy. The temperature is going to go up, the pressure is going to go up, but we're not getting any work out of it. It didn't move. All right, so that's the first leg. We're going to let it go from 30,000 joules up to 50,000 joules of internal energy right there. From B to C, I've got an isobaric process. It's just going to go straight across at 6 times 10 to the 5th Pascal, and then step C down to D, we're going to let it fall. It's going to be another isoquart process. How would we do that? Well, we'd take the heat away. We'd stop burning gas right there, or we'd take it off the hot plate, what have you. Okay? But again, we want that leg to be isochoric so the piston doesn't move. We got to grab hold of the cylinder and not let it move again, or maybe there's a little cog that holds it in place, and then when that moves out of the way, it can move. Between D and A, right here, that last leg of the journey, then we see that we've got to lose some energy, go from 45 to 30, and this is going backwards right here. So instead of getting work out of it like we did right here, right, this was the gas expanding and pushing the piston out. Right here, I have to push it back. I have to compress the gas, or the engine itself has to do work to compress the gas within itself, and that removes energy from the whole thing. So that's the 4 steps that we want to do. We know the energies at these 4 points because they're related to the temperature, and it's real easy to take a thermometer, stick it in the engine right there, and get a temperature reading. We know that the internal energy is equal to 3/2 kT. Right, so if I get the temperature, I can find the energy of that thing and see what's up. Here's the first leg. Again, the 2 questions: how much work, how much heat? So let's see if we can answer those. The work is easy because it's an isoquart process, and we never get any work out of this isoquart process. If it doesn't move, remember, work is force times distance. The distance is 0, so the work is 0. How much heat? What's it going to cost me? Well, here's the first law, and if the work is 0, then the heat that I have to add between A and B to make that change in pressure happen would be equal to the change of internal energy. Well, Q equals 50 kilojoules minus 30 kilojoules. That's the number over here. We always want to do final minus initial. So I've got to add 20 kilojoules of heat to make it go from A to B, and I don't get any work out of this thing, okay, on that step. For step B to C here, the second part of this, let's do the same thing. How much work, how much heat? It's isobaric, And I know that the work done in an isobaric process is equal to the pressure times the change in volume, so I take the pressure. I do final volume minus initial volume, and that gives me a number in Pascal cubic meters. I smile to myself because I remember that Pascal is a Newton per meter squared, and the meter squared is going to cancel 2 of these, leaving me a Newton meter, which would be joules. And probably the easiest way to put that would be 18 kilojoules. So that's how much work I get done right here. That's a pretty good amount of work. That would push your car down the road. That would grind some corn. That would do whatever it is that your engine here is supposed to do. What did it cost me? Well, to find the heat that I have to add here, remember we put a fire under this thing, and I'm paying for the whatever fuel that is. I'd have to go back to the first law and say, what's the change in internal energy? And it went from 50 to 95, so that's a change of 45 kilojoules. I accomplished 18 kilojoules of work. So on that piece, I added 63 kilojoules of energy. All right. Next up, we're going to let it fall here. We're taking the fire away. We're not adding heat anymore. We're letting this thing cool off. And this is going from C down to D. You see that I fall from 95 kilojoules of internal energy to 45. That's a drop of 50 kilojoules. I'm not getting any work done because it's isochoric and the piston did not move. And I put that 0 right here, and then I put in my change of internal energy, and you can see pretty easily that the amount of heat that I have to pull out of this thing, exhaust out of it, is equal to 50 kilojoules. But remember that we're removing that. We're taking it away. It's a negative number. That's what that negative means right there, that it's going the opposite direction. A positive heat would be putting heat in. Negative heat, I'm taking it out. Your car lets heat out all the time. There's a water pump that moves water through the engine to keep it cooled off so it doesn't melt or parts begin to expand and bind up your engine. Bad things happen. Trust me, I know. But that water goes into the radiator, and the wind blows past it, and all that heat goes down the road. We're throwing that heat away, and that's what we had to do right here. Okay. Last leg of this thing, D to A. I'm over here. Can't find there it is. Here's D, there's A. And I need to get back to my starting point so I can do the cycle again. Second time, third time, 15th time, 15,000th time. It's got to go around and around. That means I've got to end up where I started. The pressure's got to be the same. The volume's got to be the same. So how do I get it from D to A? Well, I need an isobaric contraction, isobaric compression there. How much work is that going to take? I'm having to do that because I'm moving backwards right there. Work on an isobaric is pressure times the change in volume. I'm working at 2 times 10 to the 5th here at a lower pressure. My final minus my initial is here. And you see that my work would be negative 6 kilojoules. That's me doing work or the engine doing work. Therefore, I'm losing it from the engine. And I didn't get that part. I did 18 kilojoules of work up here. I'm going to put positive 18 kilojoules because that was work I got out of the machine. But right here, the machine, or I have to do 6 to get it back to the starting point. That kind of takes away negative. Find out how much heat was removed. Again, I've got to cool this thing off. First law, change in internal energy is 15 kilojoules. It drops from 45 down to 30. So right there I've got negative 15 kilojoules. There's that negative 6 from the work that we did. You put those together, you get negative 21 right there. All right, so that's all 4 steps. We're back to the starting point. We could do it again. Let me just show you some stuff here. How much total work did we get out of one cycle here? Now, we're going to run this thing over and over again, but when you add up all the works, I didn't get anything on the isochoric process. I got 18 kilojoules out of that top isobaric process. Here I did not get any on the second isochoric as I dropped straight down, and I had to actually lose some work right there. I ended up with a net work of 12 kilojoules. On that one cycle, I got 12,000 joules of work accomplished that I did not have before. All right, and here's kind of an interesting thing. Remember we said that the work was equal to the area under the curve? And in the case of a heat cycle where we're going all the way around, we would say, well, I need the area under this, these two don't do anything, right, minus the area under this lower line. And when I do that, I get the area of the rectangle in here. And those of you that have had some calculus will recognize that as that rule that says when you have the difference of two functions, then you integrate and all that. But we're interested in the area of that. The reason, again, that the square cycle is so nice is because it makes these nice straight lines. The area is just the length times the width. So I can take the change in volume, multiply that by the difference in pressure. I'll just put P1 minus P2 or something like that. I don't know how you want to call this thing. But, oh man, I broke it. And you can see the number there that that we have. The total amount of area inside that, and therefore the work, is 12 kilojoules. So we could do it this way. We could do it this way. We'll get the same number. We could add up all the legs, how much work I got on each step, and the net work. Or I could say, give me the volume that's inside there. I don't know what this is right here, but it really needs to go away because it's bugging me. Tell you what, let's just turn the page and it'll go away. How about that? What is the net heat that enters the system? So right here we found all those heats, what it was going to cost us. And an interesting thing happens here. When I start at A and add 20 to get to B, and then I add 63, these are the numbers we found a minute ago, and then subtract 50 and subtract 21, the net heat is 12 kilojoules, the same as the amount of work that we got out of this. Unfortunately, we had to buy heat here and here, and we had to discard, we had to throw away heat here and here. So that's a little bit deceptive. We did not get the same amount of work as the net heat. It's more like this. We had to buy 83 and then throw away 71. So this is what I paid for right here. And what I got out of it was 12. Paid for 83, I got 12. All right. We could find the efficiency of this engine. How good is this engine at turning heat into work? And it's that simple. The efficiency is equal to the work divided by the heat. I got 12 kilojoules out. I put 83 kilojoules in. That's 14.5% right there. Okay. That's not a particularly good engine, is it? Well, turns out it's not all that bad either. Your car engine runs about 25% efficient. A gasoline internal combustion only turns a quarter of the heat that you put into work, into pushing your car down the road. The other 75% goes down the road as wasted heat, as exhausted heat. That's, you know, one of the things with global warming, climate change, whatever you want to call it. We are burning a lot of fuel to go down the road. If you got a big truck or a big mobile home or something, you know, even more. We don't particularly value efficiency and responsible use of energy in this country. So something to think about there. But that's the way to calculate efficiency. Now, this is the Carnot cycle. This is a lot closer to what's actually happening in your car engine. These lines are not straight lines, so they're a little bit harder to think about and to calculate. You really need some calculus to do this, and the essence here would be that you need to do the work is equal to the integral of pressure with respect to volume, and you do a thing here, and I don't know that we need to go too deep into that, but there is a process again, there is a cycle again. Right here, that first step is an isothermal expansion, so we're adding heat right here. In the case of your car engine, that would be burning gasoline, and as that happens, the piston is going to move, it's going to expand, the volume is going to get greater, and as it does that, the pressure is going to drop. So we kind of move to the right and down and end up right there. And then we have an adiabatic expansion. Remember, in adiabatic, we're not adding or removing heat. It happens either so quickly that there's not time, or we've got just enough heat there to keep that we're not adding or subtracting heat, right? It's just staying constant. It's either well insulated or it happens pretty quickly. Car engine, it does happen pretty quickly. So there's that adiabatic expansion. We've already burned the gasoline, but it continues to expand and goes out to that point right there. We need an isothermal compression, and that's when we open the exhaust valves of your car engine, and that piston comes back down and it presses that out. It's certainly not going up in temperature there, but we're not, it's happening so quickly that it's not cooling either. And gets me to here, and then the adiabatic compression gets me back to that point. All right. So again, that's a little bit harder to think about. How do we get the work? It's the area inside the curve. Okay. So we could find that area with calculus and some other ways right there, but that's gonna be the how much work we get out of it. And the efficiency of this thing, well, that's kind of hard to gauge too, except that there's this idealized way to get that called the Carnot efficiency. Sometimes it's called the ideal efficiency. In a perfect world efficiency, this is the best it could possibly be. And then if there's any friction, air resistance, anything else, then it's going to be a little bit lower than that. All right. But the idea here is that the efficiency is equal to the work over how much heat that you put into this thing, W over Qn. We're going to separate the work here into Qn minus Q out. So just as a little example, I'm going to make up some numbers here. Let's say I put 100 joules of heat in right here that gets to the heat engine, and then, I don't know, let's say 60 joules of that goes from the heat engine down to the cold sink, gets exhausted. Okay, that difference between the two is how much heat manages to turn into work over here, or accomplish work would be a better way to say it. All right, so that Qn minus Q out would be equal to the amount of work, just like 100 minus 60 would be equal to 40 right there. I'm going to take this fraction apart. I've got this denominator here, so if I go backwards, I could say, well, if I had the common denominator, then I could have this. It's easier to think about this step right here. I have a common denominator, so I could combine it there. But in math, if you can go one way, you almost always can go the other way too. So that's what's happened right there. And of course, Qn over Qn is just 1. So that's where this 1 right here comes from. And then I've got that. And remember that the heat is related to the temperature. So this thing at the end right here is what's so nice to use, because I can now come in. It's real easy to say, well, what temperature does gasoline burn at? What temperature is the outside air that I'm exhausting this engine to? And I can get those two temperatures, and those two alone give me a pretty good estimate of the efficiency of this engine. You do have to have those in Kelvin. Those two temperatures have to be in Kelvin. But if somebody walks up to you in a dark alley and says, hey buddy, what's the ideal efficiency of an engine between these two temperatures? You're going to make it out alive, okay? All you got to do is you come in here and you say, well, give me the two temperatures. And they say this is 30 degrees Celsius. That's kind of low. Let's go 130 degrees Celsius. How about it? And here we're just going to air. Let's say 20 degrees Celsius, something like that. Okay? And those would be my two temperatures. I've got T sub C for the cold temperature, T sub H for the hot temperature. And if you'll just come in here and write down your formula, like that. And what everybody loves to do is to go 1 minus 20 over 130, like that. Okay? That's not right. That's going to mess you up. These have got to be in Kelvin, and that's really the only trick here to doing this thing. 20 degrees plus 273 would be 293 Kelvin. That's my cold temperature. The hot temperature is 130. So if I add 273 to that, then I'd carry 403, I believe, is what I'm looking at right there, if I did that right. Who knows? Okay? But that would be the efficiency there. And what I could do then is just take my calculator, and I'd go 1 minus 293 divided by 403. Notice that the ones out front's got the subtraction. That's less important than the division. So it does the division first. And right there I got a 27%, 0.273 or 27.3% for the ideal efficiency. The perfect world efficiency. No friction, no air resistance, nothing that's going to divert that. If somebody steps up to you and says, hey, I got an engine that will, operate between 130 and 20 degrees, and I get 37%, 50%, you can look at them and tell them they're a liar, because that's not possible. This is the best you could ever get out of that. All right. So that's pretty easy to do right there. Don't forget about the Kelvin part, though. That's the trick. Okay. Now, got, I think, just a couple more slides here, but this one is about refrigeration. We said that heat always goes from hot to cold this way. Well, it is possible to make it go the other way, and that's what we call the refrigeration cycle. If you think about your refrigerator at home, inside, here's your milk and stuff, whatever else, your jelly, got some shelves, all the leftovers in the back, molding. Anyway, it's cold here, and it's hot, relatively hot, out in the room. And what your refrigerator actually does is it comes along and it says, I'm going to take the heat, oh boy, I'm going to take the heat that is inside the refrigerator and throw it outside into the room. I want to take heat from cold inside the refrigerator and push it outside to where it's hot. Right? Well, the whole thing runs backwards. Since the heat's going backwards, the work also has to go backwards. If you plug your refrigerator in, there is a motor, and that motor takes energy, electrical energy, plug it into the wall right there, and this thing turns, and so that's doing work. And that work is to turn the compressor. We've got an air compressor in there, and it's compressing the gas that's in there. Well, sometimes it's gas, sometimes it's liquid. All right, it's either a vapor or liquid, and it kind of changes state a couple times in there. And when it changes state, you know about the latent heat and how much heat that can absorb. So that's kind of the big part of all this. You got the compressor. The compressor is going to make that gas, let's call it coolant, That's what they call it. It's going to make the coolant hot. It's going to turn into a vapor, and I start running this vapor through the coils right here. These would be on the back of your refrigerator. And so this is hot, and as it goes to the room, it's cooler, so it starts shedding that heat. The heat naturally wants to go from these hot coils down out to the room. So I'm giving off heat all along here. All right. And then the coolant comes on around. It's cooling off. It's cooling off. It gets to this thing called an expansion valve, which is nothing more and nothing less than just a little bitty hole, and all the gas has to go through there. So as the gas gets to this point, it rushes through right there. There is a rapid expansion. You know that rapid expansions cause cooling, and so this gas, all of a sudden, this coolant gets really cold, and it goes through these coils right here, and all of this is inside the refrigerator. Oh man, can't draw for anything today. So now those are even colder than the inside of your refrigerator. So if there's a little particle there with some extra energy, with some heat, then that heat's going to come over here and bump into that super cold pipe and transfer the heat to that super cold pipe, and that coolant going through here, you can see that it's warming up as it goes. It started out super cold, but as it absorbs that heat, then it's cooling off even, as it absorbs the heat, it's heating up, turns back into a vapor, which absorbs some more heat, and then it goes through the cycle again. That's probably not the best explanation ever of the refrigeration cycle, but that's kind of how the thing works. This is the same way that your heat pump works. If you have a heat pump on your house, you've got, and let's say that it's summertime, right here it has coils outside, and there are coils inside your house, and there's a compressor and a coolant, and this same thing happens. In the wintertime, you want to go the other way. You want to take the heat that's outside and throw it inside your house, so then you just run the whole thing backwards, and these coils that are inside your house are now shedding the heat, and these ones that are outside the house are picking up the heat and throwing it inside. All right, so once again, it's the heat cycle backwards. Heat pumps don't work very well when it gets super cold outside. If it gets down in the 20s or 10s, your heat pump's going to have a hard time keeping your house warm. Okay, and that's because there's just not enough heat outside to throw inside. Okay, there is an efficiency formula for that. They don't actually call it the efficiency; they call it the CP and all these other things. We don't need to know a whole lot about that, but that's the coefficient of performance is what that stands for. But you can look all that up if you want. But that's the refrigeration cycle. All right. I have a couple of things that you probably should see somewhere, if it'll turn the page. Right here, let me tell you just real quick about reversibility. You know that if you do some work on a box, if you push a box, then the friction is going to generate some heat, right? I lose some of my force and some of the work that I do, and it turns into friction and the floor heats up. That makes perfect sense. However, I have never seen a box of its own volition, without somebody pushing it, just all of a sudden slide backwards and the floor cool off. It doesn't go this way, it goes that way. This makes sense, and this does not. It is not a reversible process. I can't do this thing backwards. It's just not going to happen. Here's another example. If I have a little cube of ice, this is supposed to be an ice cube right there, in a glass of water. So the ice cube is cold and the water is hot. Then the ice cube is going to melt and cool off the water. Right? That makes sense. We do that all the time. But this I've never seen happen. If you have a glass of cool water and all of a sudden almost all the water heats up except some of it turns into an ice cube, that doesn't make any sense. It's not a reversible process. So we talk about the arrow of time and how the arrow of time only points forward. Going backward in time would lead to some really strange results. I'm not saying it can't be done. There's lots of science fiction stuff that is fun to think about. And maybe one day we figure out how to do some of that. Hopefully not. We mess things up going forward enough. But, that's just kind of on the edge of all of what we're talking about here. Got one more term I'd like you to at least hear. This is called entropy. Entropy is a measure of the unavailability of thermal energy to do work. Remember that gasoline that we burned in our car? That made a lot of thermal energy. About 25% of it turned into work. The other 75% will no longer do work, and I can never burn the gasoline again. So in that process, I changed the heat at some temperature, and there's this number called entropy where you can calculate how much loss of usable energy there was, how much loss of structure. If I burn a log, it had chemical structure, cellular structure that took 60 years to make that log, right? And I never get the log back. I never get the gasoline back. It's gone. I converted it into light and heat and smoke and ash, but I can't put it back. The arrow of time only goes one direction. Okay? This delta S, the entropy, is equal to 0 for any kind of reversible cycle, and it's greater than 0 for an irreversible cycle. But in real life, all processes are irreversible, and so this entropy is always going up, and that's just one of those things. It's a little bit deeper than what we need to get into, but just thought you'd like to kind of think about that for a moment. Maybe it impacts the way that we think about energy and the way we use energy. We're kind of taking this resource, this dinosaur juice that we're never going to have again, and burning it up just so we can, go to the 7-Eleven and get a slushie. I don't know. Something to think about. All right. Well, thank you for your time today. If you have any questions, bring it up in recitation. That is the last video, and we're getting ready for test 1, so let's get finished with everything and get that done. Thank you very much. Have a good day.